But I'm not worried about that. I'm not worried about that. Confidence intervals will take care of that if we need that. I just want to see, is there an indication we're not in this tank anymore? Cool? Let's do it. Let's do it. We're done doing this by hand.
Yay.
Now what I'm going to do, let me do this. Let me just do this. And then we'll slide that back up. Yeah, by hand is great. I always like to start a new hypothesis test by crunching one by hand so you see where the data is falling and why. But honestly, you're going to start seeing the more we do those few by hand, you're going to see what's going on every time. It's the same thing every time. Center of the sample minus the assumed center of the population, standard error, and then you get your test statistic location. It's the same thing almost every single time. Slide this over. Okay, remind me where this is, friends. Remind me where this is. 5. Yes. Yes, indeed. So, yeah.
Can you do calculate instead of...
You can. Let's do them both. Let's do them both. Let's do them both, okay?
And that
So
gave me p hat.
it will give you p hat. Yes. Let's do both. Let's do draw first.
Test.
Because draw, let's do draw, get step 2 and step 3, finish step 4, then go back and redo the calculation so you can see your p hat. Fair enough? Okay, so p naught, what goes in there? Remind me what goes in there. Very nice. Whatever your null hypothesis proportion is, 13.5%. Fantastic. Gesundheit. X and N are going to be your sample data. So that's 121 out of 710. Beautiful.
But it's not.
Good. And then you have to adjust your sign based on what you're studying. We're trying to see if it's just changed, so make it a two-tailed test.
Yeah.
And now what you're going to see is, you're going to see two shades. You're going to see a shade on both sides. You're going to see a shade on both sides. So we'll come back to that momentarily as to why you're seeing it. Okay? You ready? Let's draw it first. Then I want to answer Beth's question about the calculate versus draw and see the difference. Okay, here we go. Oh, hang on a second. I got something turned on. Let me turn it off. Plot. There we go. Sorry, something turned on from last class. Here we go. Here she comes. Okay, I don't see anything shaded. Why don't I see anything? Alina, why don't I see anything shaded?
It's a little bit shaded.
It's so little. It's so little that I don't see a whole lot shaded because there's hardly anything there. It's so far out in the sides.
I was going to say, I thought it was...
Exactly. Well, look, that gives you an indication of where it is right there. That's a test statistic. That's a test statistic. 2.76. 2.76 what? Standard deviations. What do we say when you have bell-shaped data and you're outside of 2 standard deviations? We are 95% confident that you're an outlier, right? That's the whole point of being outside of 2 standard deviations is you are outside of 2 standard deviations. So if I look, I'm going to turn this off. The reason I like to have this curve on the board is because I like to compare the test statistic that we just got, which was z equals 2.77-ish, or 2.76. 2.76. P-value, we were going to call that p-value. 0.0057? Love it. If you want to call that less than 5%, I'm down with that too.
That's what I was going to say.
You can totally put that if you want to. Less than 5%, greater than 5%, I'm totally down with that. That's what the TI told me it was. So let's put that on this curve, shall we?
Is that a big P or a little P?
A little.
Okay, never mind.
What did you guys say? What did you guys say earlier? Margin in charge. Yes.
Oh, that bit. I'm
P
sorry.
speaks for itself, my friend. Now, we know this is 2. Well, it's 1.96, but we call it 2, and this is -2 down here, which means the tank that we have built around the 13.5% is going to go down to a certain acceptable percentage and up. We'll come back to what that percentage is momentarily, Beth, answering your question. Where did we land, friends? Where did we land? 2.77, which means we landed, what is red? So that's 2.76. 0.76, good. Basically, we landed out here. We landed there. So do we belong in this tank?
No.
Do we belong in this tank? It doesn't look like it, does it? It appears that Prevnar does result in a different rate of appetite loss because we're not landing in the tank that says it's the same. This is the tank that says Prevnar has the same rate of appetite loss as the competing medications. We didn't land there. We landed outside of there, didn't we? So it appears, if you will, it appears, and like I said, for these first couple sections, I'm going to have the hypotheses drawn out for you just like that, where all you have to do is circle appears or does not appear. You got a small p-value. That means something changed. It used to be 13.5% on the competing meds. It looks like Prevnar's different. It looks like Prevnar. What's bothering you, Ashley? What's bothering you? Just taking it all in right now.
Yeah.
Good. Keep taking it in. Keep taking it in. Ashley, go.
Could you run one property in?
Hold that thought. Please hold that thought, okay? Yes. I like following up with confidence intervals too. Just hold that thought. You're about 5 minutes ahead of me. Go ahead, Susie.
What happens if you get a dim error?
Turn your plots off. Chances are you've got a plot turned on that's trying to plot something that isn't there anymore. Yeah. Does that make sense? As far as the dim error goes, fair enough. Now, let's go back to this. Let's make sure, let's reverse engineer it back to the beginning. Here is our null curve, right there. That's our null curve. That center right there, 13.5%. Now, I don't actually have what the percentages would be. That would be too high or too small. But what it just came back studying on the hypothesis test we just did is that we got a too high result. 2.76 is too far to the right of that to accept that it belongs in here. So not only could you make the claim that the rate of appetite loss is different, you could actually say that it's higher. You could make that claim, but that's not what we were testing. We were just testing to see if there was a difference. We were just testing to see if there was more on that as we go through the course. Go ahead, Michael.
With it being that far over, wouldn't it belong to its own curve at that
That's the point. That when you say that it appears there's a difference, you are insinuating that there is another curve that it belongs on, not this one. Could we be wrong?
Yes.
How?
We say it changed.
We say it changed, but it actually didn't, which is what kind of error? False positive, very nice. Also known as, I can't imagine how loud this is right now. That's a type 1. What's the chance? 5%. Why is it 5% again? Remind me why it's always 5%.
Because we're looking for 95%.
Because we built a 95% confidence interval. Even if this thing came back at 2.01, or 2.0001, or 2.00000001, we'd still say the same thing, wouldn't we? We'd still say the p-value is less than 5%. Therefore, it appears something's changed, which means we always have the same rate of a type 1 error because we're basing the decision on 95% confidence. Is that believable? Cool. I promise you, I'll find you data sets for your assessments that don't come in that close. Although we did address that question last class, didn't we? Somebody asked me that great question, what happens when it comes in real close to 5%? And then we started finagling with the data and showing you the way to remedy that. I promise not to make you suffer through that on a timed assessment in class. I'll find you good extreme data sets. They're either well outside or well within. Here's a well outside one, right? Go ahead, Beth.
I just remembered my question.
Go ahead.
But was on the homework about the PWCs in Nebraska, like.
Good. Can you hold that till next class? Would you mind? Only because I
Can you
haven't.
hold it for me?
Chances are it's going to come up. So yeah, yes.
Okay.
I'll forget we had this discussion in 2
Isn't that
minutes.
transition from doing one way to the other?
Totally. And speaking of that, I want to answer this 2 ways. With your previous question, with Ashley's confidence interval question. I want to come back to that. I haven't forgotten about it. Georgianne, go
I
ahead.
just have a question.
Yes.
So no matter what, if it's in that, the outside, the -2 or the 2, if it's in that area, it's going to be in another curve.
Yes, that's the conclusion we're always going to make. Because if it's in that area, now, Georgianne, I want to go a little bit further. Not only if it's just in this 2-tailed, but sometimes these are 1-tailed curves. Sometimes all this area is on this side. We'll see one of those momentarily, where all 5% is over here. The key is, are you in or out? That's the key. And the decision that lets you make whether you're in or out, what's the easiest decision to make? Zoe's looking at it right now. The easiest decision to make is to look at step 3 and look at that p-value. If the p-value is less than 5%, then you are in or out. You're out of the null curve. You're into essentially another curve. 95% of the time. Of course, you're wrong 5% of the time, correct? That's the whole problem. It's probability. It's probability. You can be wrong, right? This is the whole thing. You can be wrong. I saw a hand. I thought I saw a hand. Jared, go.
Why wouldn't we just build a new tank with big data and see if it matches?
That's essentially what we did.
But like one prop Z and
Oh, good. Let's come. This is Ashley's point. So let's do it this way. First of all, okay. Grab your TIs. Let's revisit one prop Z. First, I want to revisit what Beth said to do. You may have noticed when you run this one prop z test, run this again, one prop z test. Same, everything's the same. Everything's the same. But look, instead of going to draw, go to calculate. You do get a little bit more. You don't get the curve now, but you get all of this. So you get your test statistic. You get your research hypothesis, which is kind of nice too. Test statistic p-value. It also tells you the percentage in your sample. Your sample percentage was at 17%. So 17% is significantly greater than 13.5 by virtue of the size of the margin of error. It doesn't have to be bigger than 13.5, right? If 17% had a margin of error of 5% on both sides, then 13.5 is in there, isn't it? Obviously, the margin of error on this thing is less than the distance between 17 and 13.5. And this begs Ashley's question as to what the margin of error actually is. What is the margin of error? Well, let's find out. That's when you go to your confidence intervals. Because that actually gives you the thing about a hypothesis test, it ignores your question, Susan. Not that it was a great question. But you asked, what is that margin of error? You don't need to know. It's calculating it in the back and telling you whether you're in or out of it. So you don't even have to know what it is. If you want to know or need to know what it is, then you go back to the intervals to find out. Let's find out. Let's run our one prop z int. Mine's A from before. It's already got the numbers pulled into it. Already has the numbers pulled into it. Fair enough? We go calculate. All right. So, what's the margin of error on this study? Ish. Give me an ish. Ish.
2.5.
Looks roughly that, huh? I was going to call this 14, call that 20. 6 divided by 3, call it 3. 2.5, 3. It's somewhere around 2.5 or 3, which is less than the 3.5 difference that is between 13.5 and 17. Which means the tank is small enough not to contain 13.5. 13.5 is down here somewhere. Which means you now also have a minimal measurable difference. You can say that kids on Prevnar have, what's the difference between 13.5 and 14? Roughly 1%. You could say there's a minimal measurable difference of at least 1% in appetite loss between competing meds and Prevnar. You see what I'm saying there? You now have a distance between competing meds and Prevnar. You know now how far the tanks are away from each other. Actually, go.
Is the margin of error going to be the same in the sample and the population?
Say that again.
Is the margin of error going to be the same in the population and the sample?
We can ignore a margin of error in the population because populations don't get margins of error. There is a percentage in the population of appetite loss using Prevnar, and it's one number. Are we ever going to know what it is? No. We have to accept the margin of error on our statistic. The reason 13.5 doesn't have one is because, number one, it wasn't reported to us. Number two, it's the null hypothesis. And number three, the sample has been done so many times, it's shrunk down to 0. Watch this, friends. Watch this. Friends, do this again. Stat tests, okay, stat tests. Run the one prop z int again. Run it again. But double x and double n. Double x and double n. So make 121 242 and make 710 1420. Okay? What do you notice about this interval compared to the last one? How are they the same and how are they different?
The margin of error shrunk.
The margin of error shrunk. That's how they're different. How are they the same? P hat is exactly the same because the ratio of 242 to 1420 is the same as the ratio of 121 to 1100 or whatever it was, 720, I think it was, 710, thank you. But the difference is you saw it on a larger sample, which makes the curve higher and the tails drop. And population essentially says n has gotten so big, the margin of error is negligible at that point.
Okay, there's something that is not getting.
Okay.
Why is the margin of error important if we're using a sample on the population curve which has no margin of error anyway?
Here's the deal, because your sample has variability. Your sample always has, if I just made an assumption. I just doubled everything. Everything doubled. The sample size as well as the kids with flu rates. That's kind of a fictitious assumption. Chances are, if you run the sample again, you won't get exactly 121 out of 1,000 or whatever it was, 121 out of 710. There's variability from sample to sample. The margin of error allows for the least and most amount of allowable variability. So it basically, the reason it's called a confidence interval is you want confidence. You don't want to put all your eggs in the basket that represents the middle of your interval. You want to make sure you spread that. Look at your last project. Did anybody look at the page 3, the last sheet on your last project? when you were pressing F9 and just the centers were moving around, none of them caught the actual 7.67 because there's no margin of error around those. That's ballsy, right? That's ballsy to pull that kind of crap. I don't need a margin of error. I got it right this time. No, you didn't. You can't. Most of the time, you can't. You're not going to get close to that center. So you put the margin of error to increase your confidence from 0 to 95%. Hold that, keep that kind of thinking going, Ashley. We're gonna keep re-answering it day after day after day. I promise you that. Ashley, go.
So if we're just looking for a statistical significant difference, why can't we just use one proxy? It's right there.
You can. Ashley asked a fantastic question. If you're looking for a statistical significant difference, why can't you just use one prop Z in? The answer is that one prop Z in only gives you the exact same conclusion as hypothesis test in a two-tailed test, because this is a two-tailed interval. You have to have a one-tailed interval, and your damn TIs don't have them. That's the problem. I wrote a program, basically, that created confidence intervals on single proportions and single means and double means, double proportions that were one-tailed. But nobody teaches that. And nobody talks about single proportion, or single-tailed confidence intervals. So that's where the hypothesis test kicks in. You're 100% correct. It only works, though, when you've got this situation of a two-tailed. That's the only time it's going to agree perfectly 100% of the time. Because, think about why. Think about why. Now let's make up a fictitious example. Fictitious now. Let's suppose that this test statistic came in at 1.98. Right? 1.98. Well, that fits in this curve for two-tailed. But if you make this thing one-tailed, in other words, if you take this and put it over there, it's going to slide this down. And then it's going to be out of that curve. So there are situations where they don't agree. It's one-tailed to two-tailed. That's why we can't use it except for two-tailed. Does that kind of make sense?
Yeah.
It's a fantastic question. Fantastic question. But it doesn't agree all the time unless you're just dealing with a two-tailed test. Some statisticians, friends, this is all they run. They don't ever run one-tailed tests. They just look for a significant difference. And you'll see why, as we go through the course, why that is sometimes done. But for you guys, I know you're concerned right now. How do I know which two? Do I put a greater than, a less than, a does not equals? Look for context. And after the break, we'll do a whole bunch more so you see the context. Cool? But take 5. It's getting warm in here. It's getting warm. Take 5. Get some air. Get some more. Flush the air out. And flush some more cool problems in. Yes. Keep